So today, we're going to go over, we're going to start some of the behaviors of waves. Okay, and the first behavior we're going to go over is what's called the principle of linear superposition, which is the really complex way of saying what happens when two waves are in the same place at the same time. Okay, when they are in the same place at the same time, they interfere with each other. Remember that waves are energy, not matter. They require matter to propagate, of course, but they in and of themselves are not matter. If two material objects try to occupy the same space at the same time, you get a what? Two solid objects, two material objects. You get a collision. Okay? Waves don't collide. They can physically occupy the same space at the same time. But waves are energy. And when you put more energy in one place, that medium in which the wave is traveling has to show that that much energy is there. What part of the wave represents the energy of the wave? Which wave property? It's the amplitude. So when two waves occupy the same space at the same time, the amplitude in that space will change to reflect the amount of wave energy that is there. Okay? That means it could get, the amplitude could get greater, or the amplitude could get smaller. It depends on what type of interference is going on. When we were watching that crappy little video that I took in Jamaica, okay, of the waves crashing on the shore, every once in a while we got one wave that was bigger, okay? And that's because the waves that were coming in were up, and the reflected wave that was going out was also up, okay? And when those two waves occupied the same space, instead of having an amplitude that's this much, the amplitude had to be this much, okay? It had to be as much energy as was in that space. That means the energy of both the outgoing wave and the incoming wave, because they were occupying the same space at the same time. All right? Everybody follow me there? This is how we amplify sound without using powered amplification. You know, if you have an electric guitar, you plug it into an amplifier and you amplify the waves produced by the strings, but you use power to do it. An acoustic guitar makes the same sound when you pluck the strings, but it's way louder than an electric guitar that's not plugged in. What's the difference?
Because the acoustic guitar, the waves travel into the guitar, bounce around, amplify inside, and fly out.
Right. They amplify inside before they come back out. And the way that they amplify, the shape of the guitar is such that it can channel waves to make them interfere constructively. That is, make the amplitude greater. Because many waves are produced by an oscillating guitar string. Okay? It's not like you pluck it once and it makes one wave, it makes a whole bunch of waves. Okay? All those waves enter the acoustic chamber of the guitar or any other string instrument for that matter. Okay? And they can bounce around in there a little bit and interfere constructively and then have a greater amplitude when they come out. Okay? Almost all musical instruments that are acoustic use some version of this to produce sound, or louder sound that is actually just produced by the initial vibration.
What kind of math goes into the construction of one of those acoustic spaces?
Oh, a lot. I was actually just trying to research the acoustic design of the Winsphere Center in Edmonton, okay? Because it's this like almost acoustically perfect building where you could have a concert on the stage and not require powered amplification. And people would hear it, it would sound incredible, simply because of the shape of the concert area. They've got like curved reflectors in all these different places in the thing, but I could not find anywhere, kind of a architectural design diagram that explained how they did it. Okay, I only know, kind of my weak knowledge of architecture. I can look at it and go, oh yeah, that's definitely for channeling waves. That's definitely for reflecting waves. But how they get every person in the whole building to hear good sound in every seat, that's why they make the big bucks. I don't. Okay, but yeah, it is like it was a triumph of design when it was first built because it was so acoustically perfect. Okay? But it is a small venue, right? It's not like you're going there to watch, a concert with 25,000 other people. It doesn't seat that many people, right? If you go to a concert at the Saddle Dome, okay, which is like one of the most acoustically How do they make it so that it's just really loud? Tons of speakers, tons of powered amplification, okay? And there are gonna be dead spots all over the place in that building, okay? Like acoustic dead spots where you would hear some sound that would be very good and other frequencies or wavelengths that would be not so good, okay? It all depends on where you are. In the wind sphere, apparently, I've never been there, okay? But apparently in the wind sphere center, there's not a bad seat in the house. Every place you sit, the sound is good. Okay? Now that would take a lot of know-how, and acoustic engineering and all of that kind of stuff to make a building that is like that. Okay? It's kind of, it was really ahead of its time when it was built. Okay, so that's what we're going to look at is basically interference, how it works. I wish I had a better answer for you. It's kind of above my pay grade. I wish I knew more about it. Like I said, I was trying to learn a little bit about it this morning, but I couldn't find anything. I would think that for proprietary reasons, that type of stuff is probably kept on the QT, right? So that they can use it somewhere else, maybe get paid again to make another building like that. All right, understand what happens when two waves occupy the same space. Well, they interfere. Okay? I'm sure you have had this experience. Okay? You have dealt with interference. Now, we always associate interference with bad. Okay, well, I've got interference, I can't, my call got dropped, or I can't send a text right now, or whatever, okay? When, in fact, interference can be both constructive and make it better, like an acoustic instrument, or destructive and make it really loud, so this is the one that we're most commonly familiar with, okay? So the two types of interference are obviously constructive and destructive. One makes the amplitude greater, constructive. One makes the amplitude smaller, destructive. Okay? And how this can be applied to practical uses. So obviously the wind sphere center is a practical use. The design of all musical instruments has a vibrating column of air that is causing interference that amplifies the waves. We'll learn about air columns later on. But yeah, there's lots of practical uses. The muffler in your car, okay, uses dampening, which is sort of like interference. It makes the waves bounce around a lot and lose energy and interfere. And when it comes out the tailpipe, it's not as loud unless you're one of those people who cuts your exhaust off just past the headers. That guy. Yeah, you can hear from a mile away and should have some sort of noise complaint against them because they've got the really loud truck. So stuff like that. If the muffler does a certain job, it deadens or dampens or destructively interferes all of the waves that come out so that it's quieter. Okay, and there's a whole science behind designing mufflers to make cars sound really good. Okay, by channeling the waves, not having as much dampening, okay, so that they come out and they sound nice. Okay, then there's just loud, and then there's nice and loud, and then there's nice and quiet, and then there's just quiet. Right, all of them involve kind of different science. Okay, making sense so far? All right. So, straightforward way to deal with situations in which two or more waves occupy the same space. We said waves can do that because waves are energy, not matter. Right? The simple rule of the principle of linear superposition is add the amplitude of the waves, and you will have the resulting shape. Right? So, on the left here, we've got an example of constructive interference. Okay? Wave A is traveling to the right, wave B is traveling to the left, and when they begin to overlap or occupy the same space, the slinky takes on the shape that the sum of their amplitudes would show. Okay? In this case, it's double. Right? If B was half the size of A, then the resulting wave would be 1.5 times the size of A. It would be the sum of the two amplitudes. Okay? Because it's kind of conservation of energy. I would add the energies together to show or represent how much wave energy was present in the medium. Right? On the right here, we've got destructive interference. So wave A is coming in, it's got a positive amplitude. Wave B is coming in, it has a negative amplitude. When they overlap, there's nothing. Okay? Their wave energies cancel out because one was positive and one was negative. So at that instant, and only for that instant, the waves appear to be gone. Are they? No. They'll go right through each other and keep right on going. Okay? They have their energy, remember, not matter. This isn't a collision, it's an overlap, and then they just go right on just fine. Okay? If we want to make waves interfere and stay interfering, we have to kind of change their direction and channel them together, which is what closed and open air columns do and what acoustic instruments do. Okay? So in this case, they just pass right past each right? Everybody with me on that? So, a couple of years ago, I took a slow-mo video of this. Okay, we had a Slinky, and I'll bring the Slinky out and we'll do it for real, but it's easier to see when we can slow it down. You can actually watch the Slinky do its thing. Okay, so I'm going to show you that right here. Okay, so we've got two waves that are opposite. Okay, and you can see that for an instant, they had completely canceled each other out. These are the reflected waves going back towards each other. Okay, I'm just gonna bring it back here. Oh, it's not gonna let me do the slider. And then we'll do one where they're, I think, the same direction next, so we get constructive interference. Didn't seem like that long a wait when we took the move. Boy, slow-mo makes everything take so much longer. Okay, so now we've got two that are the same amplitude going towards each other. And then they just go on about their way as though nothing happened. All right, so like I said, it's a little easier to see when you can slow it down. Okay, you can really see that Slinky just suddenly it's disappeared, and then suddenly there the waves are again. Okay, or there it's double, and then there the waves are again. They don't get affected by interference. Okay, because we have this idea that interference is permanent and oh, it's all gone, because our experience with interference tends to be with our electronic devices. And well, that moment in time has passed, and I missed my phone call, or I didn't get that text message, or in my case, I had an old Wi-Fi router that was, I don't know if anyone has one of these like older Wi-Fi routers that's on basically the same frequency as your microwave. If you fire up the microwave, the Wi-Fi goes out. Okay. Because I didn't know this until I was streaming March Madness. So I had like 5 different devices streaming the 5 different games in the opening round that were going on at the same time. And like 2 of them were in crunch time, and one of them involved my team. And I'm watching it, and then the kid goes and throws something in the microwave, fires out like, no! Everything went out, right? Except the cable, and anything was connected on the wire was okay. But of course the device I had streaming the game I was interested in goes down, because suddenly the waves from the microwave, which are on the same wavelength, okay, as the ones coming from the Wi-Fi router, they start interfering, and I get no signal. I mean, there's still waves there, but at the point where the receiver is, they're all jumbled. Because now there's waves coming from 2 different sources, the amplitudes are going all over the place, the receiver doesn't know what to do about it, and it just goes, I give up, and it quits. Okay? It says no signal until I run over and smack the microwave off, okay? And everyone's cheering, and it's not my team that's cheering, and I missed it. Okay? Yeah, that's what happens. Okay, so that's interference. Like that's 2 waves in the same place at the same time. If you've had this experience, you might, you're talking on the phone and the signal's bad, and you're like, can you hear me now? Can you hear me now? And then you take 2 steps to the left and suddenly everything's fine. Okay? That's because the point you were at, that position right there, there was some other set of waves that were interfering destructively, and all you had to do was move a wavelength, a half a wavelength away, and suddenly it was fine. Okay? You go to a different spot, and suddenly that interference is no longer there. Okay? It's kind of weird, but it's how it works. Okay, everybody with me so far? All right, so in the diagram on the right, that's constructive interference, okay? So it's the sum of the shapes of the individual pulses, okay? And that's constructive interference. This is destructive interference, so the waves try to overlap. When they overlap, their amplitudes cancel each other out. There's no amplitude until afterwards, and then they go on their way. I almost always ask a question on the unit exam. Can you draw me a picture of 2 waves before, during, and after complete constructive or complete destructive interference? So being able to draw a diagram like those 2, it would be something I would certainly ask. Okay. In fact, I think the last test, I did it a little bit differently on the last test. So what I had was kind of like this, and I drew two waves. I think I drew them like this. I said these two waves are occupying the same space at the same time. Draw the resulting shape or the resulting waveform. Okay, is this going to be constructive interference or destructive interference? It's going to be constructive. These waves are what we call in phase. Okay, that means when one is up, the other is up. When one is down, the other is down. They are in phase, doing the same thing. They also have the same wavelength. Okay, so since they're in this position and in phase, okay, the resulting waveform would look like this. Right, now, I put it on graph paper on the test so that people could actually add the amplitudes like together. It was like 2 and 1, so it should be 3, okay, something like that. Or I could put them so that they were opposite, and then it would be destructive, and you'd have to draw it smaller. Okay, but that's kind of the application that I would be looking for on an exam. Okay, I'd be looking for the right shape for 2 marks and telling me whether it was constructive or destructive for 1 mark. It's kind of a gimme question. All right, is anything ever that simple? No, I can always find a way to make it a little more involved. Okay, and we're going to do that. Okay, so, sorry, this is just the part about destructive interference. 2 opposite pulses overlap, okay, then they momentarily cancel. The slinky would appear straight for a short period of time. In either case, the 2 pulses move apart after overlapping, and the slinky once again conforms to the shape of the individual pulses. Okay, that is the principle of linear superposition. So if I ever use that term, principle of linear superposition, you know you're adding the amplitude of the waves. Okay, so these are wave trains. Can wave trains also show this? They sure can. Okay? It doesn't matter how many waves there are, they can interfere with each other. Right? On the left, okay, we have wave A and wave B. Are they in phase? Yes. When one is up, the other is up. When one is down, the other is down. They are in phase. So that would be an example of constructive interference, and a resulting waveform would be underneath, just like what I asked you to do a minute ago. Now, in the second situation, are those waves in phase, wave A and wave C? No, they are 180 degrees or completely out of phase. When one is up, the other is down. Okay, that would be an example of destructive interference, and the resulting amplitude would be still the sum of the 2 waves, but now a decreased amplitude. And we would, if this was a sound wave, detect this as a decreased volume. Okay, if it was light, less intensity to the light. Okay, everybody's good with that idea? Now, those are all one-dimensional waves, waves on a slinky. Okay, now, I think before we get into 2-dimensional waves, I'll bring out the Slinkies, and you guys can put them between the rows, and you can just kind of experiment with this a little bit, kind of do this for yourself, and kind of see how it works. Just sometimes it's, you know, better to see and do it yourself a little bit. So we'll bring the Slinkies out, and you guys can have a little bit of time with those. Okay, remember, treat them gently. They are a scientific instrument, not a toy. Okay, the toy ones are short. These ones are really long. Okay. All right, so we'll have a little bit of time with those. So, next thing we're going to look at is like a more realistic situation. I mean, the Slinkies are fun, but those are one-dimensional waves. Okay, there's not much to it. What we're going to look at now is kind of like the situation we have on the board with these 2 speakers playing the same tone. Okay, so it's the same sounds, the same frequency, and they're just playing it constantly. Okay, kind of just a long beat. Okay, but it's just that's that one tone the whole time. If this person is the same distance from each one of those speakers, he should hear a loud sound, because the waves will arrive in exactly the same point in the wave from each source. Okay? And the same would be true with the 2 tuning fork resonance boxes I've just put together over on the side. I haven't done this demo for a long time. This box is really dusty. But we're going to try it. It doesn't always work. Okay? Why would the situation we have there on the board not work in a room like this so well? Okay, it's not a perfect square, for sure. And what is there gonna be a lot of off the walls? A lot of reflection and echoing, yeah. Okay, so you don't always get the truest sense of this. If you do this, what we're about to do, in an anechoic chamber, which is a scary place because it looks like you're inside a meat grinder. Okay, like the walls are all different, like pointy shapes and stuff, because it keeps the echoes from coming off the walls if they're irregularly shaped. In the band room, for example, they've got the padding on a lot of the walls. That's to keep reflections from coming off the walls, making it more anechoic or more acoustically sound. Okay, in here, well, I don't have that. I got whiteboards, which are perfectly smooth and the exact opposite of all of those things. So, okay, we'll give this a try. If we stand in a position where we're equidistant from these two things, and this one looks like it's been deformed, but we'll give it a try and we'll see. You guys can kind of get up and move around quietly, or you won't be able to hear the tone. But
It's a nice chord.
It is, but they're supposed to be the same. They both say 256 hertz. That's middle C, by the way, because you all do that. All right, let's try it again, even though they sound different. We'll try it anyway. Okay, so just kind of move about the room and see if you can find spots where it's quieter and louder. Okay, you find a dead spot?
yes, that's great.
Okay. Whoa, I hit the wrong part. Swing and a miss.
The C is really loud. When it's gone
Okay, are you finding a few spots where it's a little louder and a few spots where it's a little quieter? Okay. All right, have a seat. That's gonna sound really cool on the mic. Okay. So, what we're doing here is we're essentially having two sources that supposedly, they don't sound like it, but supposedly have the same frequency and the same wavelength. Okay? If that's the case, then they're making identical waves. But there are going to be places in this room where those waves arrive in phase. That would be crest to crest and trough to trough, or since they're sound waves, compression to compression and rarefaction to rarefaction, and producing constructive interference. Okay? Those spots you might not notice as much as the quiet spots, where we're getting destructive interference and the waves are meeting completely out of phase. Okay? But there are equal numbers of constructive areas, okay, and destructive areas, okay, or nodal points, okay, or antinodal points. Right? Those are the constructive. Antinodal are constructive. Nodal are destructive. Okay? So obviously for this person, because the sound waves have traveled the same distance from each speaker, they have also traveled the same number of wavelengths from each speaker. Okay? So there's going to be crest, crest, crest from that speaker and crest, crest, crest from the other. He's standing at the position where they're meeting crest to crest or trough to trough. Okay? Always. Now, obviously, the loud places and or let's just say the loud places for now, are not always going to be in places where you're equidistant from both tuning forks. Okay? How is it that you can hear this like a louder sound even though you're not the same distance from the two tuning forks? Right. It's a whole number. That's the key. Okay? If I back this up a full wavelength, which in this case is 1 meter, he'd be further from this speaker here than he would be from that speaker, but he would still hear a loud sound. This one will have traveled 4 whole wavelengths and still will be a crest at this position. Okay? What matters for whether you hear a loud sound or a quiet sound is whether or not they're meeting in phase, not whether they've traveled the same number of wavelengths. As long as they're still both a crest or still both a trough, you'll hear a loud sound. Okay, if I back this speaker up a half a meter, or half a wavelength, then one set of waves will have traveled 3.5 wavelengths, and the other one will have traveled 3 wavelengths. Now they'll be arriving crest to trough, and we'll get a nodal point. Okay, sorry, someone was about to raise their hand and ask a question.
Yeah, so it doesn't matter how far you are away from the sound sources as long as they meet up,
How they meet up.
like how they meet up.
Yeah.
So the further and further that guy moves away from the speakers, as long as he moves that 1 meter, he's always going to hear the same volume.
Not necessarily the same volume, but he'll get to a point where it's obviously louder than one step to the left or right.
Okay.
Yeah, because obviously sound diminishes with distance, as all forms of energy do, right? It has to fill a 3-dimensional space, so it's decreasing exponentially as you get away from it, right? When you stand right there, it's really loud. Got to the other side of the classroom, considerably quieter, right? So, no, it's just gonna be, oh, there's an area where obviously 2 waves are meeting crest to crest. Here's an area where they're obviously not meeting, okay? But yeah, it's not gonna be that it's always gonna be super loud, it's just gonna be louder in that spot, okay? The further away you go, the quieter that's still going to be, if that makes sense. All right, so if we have 2 speakers and they're producing the same tone, this is what we're kind of looking at as in a 3-dimensional space, what we had in the classroom. There were some places where they met crest to crest. Okay, there were various places throughout the classroom where that was true. Okay, and we heard a loud sound. And then there were places where it was quiet. That would be like here. It's exactly 2 wavelengths from this speaker, but it's 1.5 from this speaker. So this would be a trough. We didn't draw the troughs in here, we just drew the crest, but a trough would be halfway between them. Right? And so that would be an area of destructive interference. Everybody all right with that? So if you've only got 2 sources for the sound, there are going to be dead spots. Okay? There's just no way around them for that particular wavelength. What if I change those tuning forks and use different tuning forks? Would there still be dead spots?
Yeah.
Yeah. Would they be in the same place? No. Okay? Because that it would be a different frequency and thus a different wavelength. So those dead spots would be in different places. That's the difficulty in designing an area that you want to have every, like let's say like the Winsphere Center, where you want every seat to sound good. Well, some of those seats for some wavelengths are not going to be good, and some of those wavelengths for other seats are not going to be good. If it's anechoic, like that means no bouncing off the walls. But obviously, there's going to be some reflection off the walls, and they actually can harness this in the shape of the design. Okay, they can have different wavelengths bouncing off the walls or the ceiling in different ways to kind of fill in the dead spots a little bit. Okay, in a movie theater, they don't do it that way. It's still shaped like this, like like an amphitheater. But in order to make sure there's no dead spots, there's a lot of what? Also padding and speakers. Yeah, just put more sources for the sound. Okay, now it becomes again a little bit more challenging if you're trying to do surround sound, because then you have to have some sounds coming from behind or to the left or to the right if it's in stereo, okay, and it has to sound that way. So there's a lot of engineering that I don't fully understand, okay, that goes into getting these things to sound right, okay, and we kind of take it for granted because it's just cool, okay, but yeah, there's a lot of engineering that goes into it.
So when you were talking about surround sound, that reminded me that some old DVDs I have in my house, they have Dolby surround sound
Yep.
on them.
Mm-hmm.
How does that work only coming out from one speaker?
It doesn't. Yeah, it doesn't work.
So it's
If you only have one source for the sound, there's no way you could make it sound like it was coming from behind you unless you had designed the room to do something really funky. Okay, and maybe you could do that. I don't know how. Okay, there's different kinds of surround sound as well. Right, there's like the first kind of surround sound was 5.1, which meant you had a center channel that basically played the voices, the dialogue, and then you had 2
front speakers that produced sound effects and things like that. And then you had two rear speakers that gave you the illusion of sound coming from behind. And the way that that would be coded into the sound, I guess, on like a digital DVD or something like that, would be that these signals go to these speakers, and you have to have a receiver that can understand that code and go, okay, these frequencies go to these speakers, these frequencies go to these speakers, and this frequency goes to that speaker. And you can set it up where you can delay certain frequencies, so if it's a sound coming from a certain speaker, it comes out a little later or something like that. I just remember playing around with that with my receiver one day. Okay, and it can help to fill in, again, those gaps. But like if you are a person who designs those kinds of things, you fully understand that you'll be able to program it. Probably take me 10 years to figure out how to do it. Okay, with someone who that was their line of work, you'd be able to do it pretty quick. A few measurements and it help. Okay, so that's kind of the challenge with all sound, is that there's going to be some places by their very nature, just because they're positioned, that are not going to be good for this frequency, not going to be good for that frequency. Okay. All right, so if it was destructive interference, then, like I said, we back this speaker up 0.5 meter, and now suddenly the number of wavelengths from this speaker is 3.5. The number of wavelengths from this speaker is 3. The difference is half a wavelength, and it's about the difference. Okay? If the difference in travel is a full wavelength, 1, 2, 3, 4, 25, 50, you're going to get constructive interference. If it's half a wavelength off, so 0.5, 1.5, 2.5, 75.5, okay? As long as it's a half, you're going to be in a point where they're half a wavelength out, and that's going to be destructive interference. Okay? Everybody with me on that? All right, so here's the kind of thing that we would run into, right? We still got our two speakers here, okay, and they're playing just a tone, not like a movie or music or something like that that has lots of different frequencies and wavelengths in it, okay? Just a single tone. These would be great spots to be for that tone, because that would be where waves are lining up and interfering constructively. These two spots would be bad, okay? Because for that frequency and wavelength, it's not. Okay? And you got to remember that this can also be affected by temperature. If I change the temperature a few degrees, I change the speed the waves travel at, and those spots move. Because their wavelength changes when the speed changes.
So when movie theaters are usually cold?
Well, I mean, they have to have temperature control for a bit of sound, but mostly I think it's just comfort. Yeah, it's easier to put on a sweater than it is to, take off layers in the theater. Yeah. So, yeah, I mean, before I had air conditioning, I would just go see a movie on hot. I couldn't answer you on that. I mean, they have to keep a consistent temperature, but if that's done on purpose for sound, I couldn't tell you. Okay. And you'd have to change the temperature, significantly to notice that, but yeah, it's there, right? If the temperature changes, that's going to change. Those spots are going to move a little. Okay, so here's the kind of thing that I often ask, okay? Like, I always have a question like this on the unit exam. Sometimes I put one on the final, right? So I want you guys to copy this one down, okay? The two loudspeakers, and we're going to walk through how to solve it together. Okay, so I've got these two loudspeakers, speaker A and speaker B, okay? So this will be, 2-point direct. Okay, so this is speaker B, and this is speaker A. Okay. So both speakers are playing identical 214 hertz tones. Okay, and the speed of sound in that room is 343 meters per second. Didn't want that to bounce up, I wanted it to go away.
So what we learned so far today is that where that person is and the wavelength of the sound is important for determining whether or not they hear a loud sound or a quiet sound. If they hear a loud sound, it's because the waves have traveled whole numbers of wavelengths, okay, or actually not so much whole numbers, but the difference in the number of wavelengths traveled from each speaker is a whole number if they hear a loud sound. If it's 0.5, then they hear a quiet sound. What if it's somewhere in the middle? Yeah, kind of normal, you wouldn't really notice. I would never give you a question where it was somewhere in the middle. Okay? It's either going to be clearly half a wavelength or clearly a full wavelength. And I mean by clearly, I mean like it's 1.03, that's a full wavelength. Okay? If it's like 1.2, then I just designed the question terribly. Okay. All right, so let's have a look at this. First thing I need to find out or calculate for this question is what? The wavelength? Yeah, okay? And I was actually thinking one other thing, but I can calculate them in either order. There's two things I gotta know before I can do anything with this question, okay? And the first thing is I need to know the wavelength, okay? Well, wavelength is speed divided by frequency, okay? Just manipulating the universal wave equation. If you recall the other day, we're gonna use this thing all the time, for an example, okay? So, we got 343 divided by 214. I think it comes out to 1.6, yeah? Yeah, okay. So 1.6 meters is our wavelength. All right, I need one more thing before I can go any further.
The hypotenuse of the triangle.
I need the hypotenuse of the triangle because I need to know how far it is from A to the observer. All right, so 3.2 squared plus 2.4 squared, this comes out to 4? Exactly 4, right. Okay. I know the waves are 1.6 meters long. I know how far the waves travel in meters from each speaker. What do I need to know between the speaker and the observer for both speakers? The number of wavelengths. How am I going to find that?
You take the distance and divide it by the length with one wavelength.
Right. Take the distance divided by the wavelength. That'll tell you how many waves there are between that speaker and the observer. Okay, so if I go 2.4 divided by 1.6, I believe that gives us 1.5 wavelengths, yes?
Yeah.
Yeah. Okay, and 4 divided by 1.6, I believe, comes out to 2.5 wavelengths, yes? Okay. Okay, so what we did there is we needed to find the number of wavelengths. So we took the distance and divided by the wavelength. Okay, so in this case it was 2.4 divided by 1.6, and we got 1.5 wavelengths. And then we did the same thing over here, went 4 meters divided by 1.6, and we got 2.5 wavelengths. Okay, does the person hear a loud sound or a quiet sound? Loud. 2.5 divided, or 2.5 minus 1.5 is 1. That's the difference is 1 full wavelength. It's the difference that counts, okay? Not the number of wavelengths, but the difference in the number of wavelengths. If it's 1 whole wavelength, or 2 whole wavelengths, or 5 whole wavelengths, they're still arriving at the same point, or in phase with each other. Okay? So in this case, even though both sides are a half a wavelength, the difference in travel is still a full wavelength, and thus this person hears a loud sound. Okay, and I did that on purpose, just so that we can illustrate that, yeah, because if I do this with 3 and 2, it's obvious. Okay, but with 1.5 and 2.5, it makes us think, because we said, oh, if they're half a wavelength out, it's destructive. Still true. The difference is 1 wavelength in travel. One of them goes 2.5, the other goes 1.5 wavelengths, so they're still arriving in phase. Okay, that's right too.
I might have just heard it incorrectly, but didn't you say before that if the number of wavelengths traveled is a whole number, then the sound is loud?
The difference in the number of wavelengths is a whole number. Yeah. Okay, does that make more sense now? Okay. So we always take whatever the wavelengths are on both sides and subtract them, because it's the difference that matters. Okay, if this had been 3 wavelengths and this had been 1.5, then they'd have heard a quiet sound because the difference would be 1.5 wavelengths. So one would be a trough, the other would be a crest. Okay, these are still arriving at the same halfway point in the wave. Yeah. All right. So there has never been a unit exam where a question like this or this question has not been on it. Okay? For this reason. It asks about wave behavior, it asks about interference, it makes you use the universal wave equation, okay? It allows me to test a number of things in one question to make the test a little bit shorter. Okay? Because I'm not going to give you a question that's just about using V equals F times lambda, but I can throw it in here. Okay? And you can show me that you can use it. All right. So don't have the other stuff in here that I wanted. Okay, let's take a little break here while I find the other stuff that I thought I had in here. Okay, so I'll give you 5 minutes here. So interference is just one example of wave behavior. It's what happens when two waves occupy the same space at the same time. But obviously waves can do more than that. Okay? When you guys were making waves with the Slinky, you probably observed that when you made a wave towards the other end, it bounced back. Okay? Well, that's just another behavior of waves. They reflect. Okay? Now, that's not, earth shattering, so do particles. If I roll a particle at a wall, like a ball at a wall, it bounces off the wall, comes back. Okay? No different than waves. What we're going to look at here is some of the behaviors of waves that are the same as particles, and one that only waves do that particles do not. Okay? And it was actually pretty important because it led to the discovery that light is not a particle. Light is a wave. And then later that wave is both. Or that light, is both a wave and a particle. Okay? But for a very long time there was a lot of debate about the nature of light being a wave or a particle. And then, just to make everybody happy, we just said it's both. But in actual fact it is. All right, so we're going to look at what happens when a wave encounters a boundary between two media. Well, when a wave encounters a boundary between two media, lots of things happen. Okay? Anytime you reach a boundary, some of the wave is going to get through, and some is not. Okay? We call that partial reflection. Some of it's going to come back, some of it's going to get through. What determines how much of it comes back and how much of it gets through is how similar or dissimilar the two media are. When you were making a wave in the Slinky towards your partner who was holding the other end, it was trying to travel from the Slinky into a person. Those are two very dissimilar media, which is why most of the wave got reflected back. Okay? But if I'm going from, let's say, water that's a meter deep to water that's 90 centimeters deep, is that a big transition? No. Those two media are very similar. Okay? So the more similar two media are, okay, the less reflection there will be. Okay? If I hook two Slinkies together, there's still a boundary between Slinky 1 and Slinky 2, but if they're the same style of Slinky, it's like nothing's going to happen. Okay? They'll go right on through because the boundary is really not a boundary. The media are essentially identical, okay? And almost nothing will happen at the point where they're connected. That sort of makes sense? Right? A place where we see this kind of happening is often with light. Okay? Sometimes you can see this with like the color of the sky a little bit. Okay? Light gets scattered with different natures of the air. Most of the time the sky is what color? Blue. Okay? Sometimes it can be different colors, like at sunset and sunrise, right? It's orange. Why? Not so much more, but what's in the air?
Sun reflects on clouds.
No. I mean, it does that, but that's not what makes the sky orange. Because sometimes it's orange in the middle of the day. Like a few years ago, we had all those forest fires. Anyone notice that? The sky was like literally orange. Okay, they had the video from that Lytton. You see there, the one that the whole town
town burned to the ground there last summer? Okay, that when they had pictures of the people coming out of the town, like the sky looked orange, and it was in the middle of the day. And it wasn't because of the flames in the background, I mean, that's part of it, but, it looks orange because there's so much particulate in the air, close to the ground. Okay, so it looks a different color. I don't know if you guys have ever noticed this, but sometimes when you drive towards Calgary, there's this brown layer above. It's called photochemical smog. Okay, and it means that there's lots of particulate smog, okay, that's at the ground level, okay, and when the sun hits it, it scatters the brown wavelength of light instead of blue, and so we get this layer that appears brown. At dawn and at dusk, okay, we're going through more particulate, okay, things like that, and so it changes and scatters the orange and red wavelengths, so we see that color instead.
But the air quality, or what's in the air, isn't substantially different from the morning to the middle of the day. So how does that change the color?
Because when the sun is at a low angle, it's traveling through air that's closer to the ground, that is going to have more particulate, because particulate is heavy, so it's going to be closer. When the sky is overhead, or the sun, sorry, is overhead in the sky, he's coming straight down. So when we look up, we don't see that, right? So, and when it's really smoky, then the sky appears a different color because the particulate is everywhere, right? And so it scatters different wavelengths, and the sky appears a different color, right? That sort of makes sense, everybody? Okay, so lots of characteristics of a wave change when it enters a new medium. Speed changes, wavelength changes. What doesn't change? Frequency. What else can change? What's that? Oh, I just can't hear you.
I think I'm wrong.
I don't think so. I thought you said amplitude.
Yeah.
Yeah, you're right. That's the third one. Okay, wavelength, speed, and amplitude can change because amplitude represents the energy of the wave. And if it goes into a new medium and some of it gets reflected off, there's not as much energy, so the wave's not going to be as tall. Okay, amplitude can also change because if the speed of the wave changes and it slows down, the back of the wave catches up and the amplitude goes up because the wave got shorter. Okay, if a wave goes from a slow medium to a fast medium, when the front of the wave gets into that, it takes off. It runs away from the back of the wave, stretches the wave out, and the amplitude goes down. Okay? So there's all those three things can change when a wave enters a new medium. The only thing that doesn't change is the frequency of the wave. Okay? All right. So waves can travel through lots of materials, but it does so at different speeds. It's the medium that dictates the speed of the wave. Okay? When light passes from one material or medium to another, its speed changes, and that can lead to a change in direction. So, we have some boxes of toys in the back. I mean scientific instruments. All right. Colin, can I get you to turn both sets of lights off there, please? Thank you. All right. So, what I've got here, okay, is just a semicircular prism, okay, and I've got just a little laser pointer. Okay, I'm not going to shine it in my eyes because it's bad for your eyes. I won't shine it in your eyes either. Okay, not like that fan at the hockey game who like tries to put the laser in the goalie's eye. He's got big trouble. Okay, it can cause cataracts. Very bad. So, if I have, wrong button. Okay, so I've got this laser. It's going into the. See how when I change the direction of the laser, it changes where it comes out? Okay, and I get some reflection. Okay, I get some going through. Okay, well there's actually an angle. And you see how when I have a certain angle, the light can come through, come out the bottom. But if I change that angle enough, it only comes out the top. Okay, that's that thing we were talking about with the stone cutting, with cutting a diamond the other day. Okay, you get that angle right and it can't come out the bottom. Okay, same idea here.
But obviously it travels slower in the prism than it does in air, right? And so it changes the angle at which it travels. Okay? Now, that only happens if it comes in at an angle. If it comes in straight on, and I do it right, okay, it doesn't change it at all. It only happens if it comes in obliquely. Okay? Then it gets changed. Right? We call that refraction. Okay? Just has to do with that you can also change the direction of a wave, okay? If it comes in obliquely. You're changing the wavelength, you're changing the speed, you're changing the amplitude, and you can change the direction if it comes in at an angle. All right, and so that's what they're showing you in the first diagram. Thanks, Glenn. You turn this back on. Okay. When we had those light waves, sorry, all right, so when we have these waves coming in, if these are light waves, and obviously they're not because they'd be way closer together, okay, when it comes in at an angle, part of the wave encounters the new medium before the rest. So it slows down and falls behind the rest of that wave. Okay? And as the wave continues to travel forward, more and more of it gets into the new medium where it gets slowed down, and that pulls the waves in this direction. It makes them bend and change direction. The same thing happens if you're running along and you stick out your arm and it catches a pole. Okay? That part of you slows down. This part of you keeps trying to go fast, and what happens? You turn, you rotate around the pole. Well, the same thing is going on here. As these waves are coming into the new medium, this part catches and slows down and pulls the rest of the wave around. Okay? Changing its direction by refraction. And so we can see this sometimes with, like if you put a straw in water, looks like a bend, but it's really not. Okay? Anyone ever tried spear fishing? I haven't either, but I want to try it sometime. Okay? But apparently it's really, really hard because where the fish appears to be is not where the fish actually is. The fish appears shallower in the water than it actually is because when the light waves come out of the water, they change direction. Okay? And so they make it appear like it's shallower. So if you aim for the fish, you miss. And they're always closer to your feet than you think. So I guess it's hard to stab at your feet or something. Sure. Okay, is that making sense? Right, so speed can change, wavelength can change, and amplitude can change, direction can change if the waves come in at an angle or oblique. All right, so wave energy that's incident on a boundary between two medium can either be transmitted to the next medium, reflected off the interface, or both. Okay, that's rarely all or none. Okay, most of the time some of the energy is transmitted, some is reflected. This is known as partial reflection. Unless you have something that completely reflects waves, okay, there's always going to be some that goes through. Right, the determining factor, as I said before, as to how much of that wave energy actually gets reflected or transmitted is the similarity. If the two media are very different, there's going to be a lot of reflection, okay, or transmission. If they're very similar, then most of it will be transmitted through and there'll be very little reflection. Okay, so if we're looking here, okay, at this diagram, so I've got a wave traveling through a very dense medium and going into a less dense medium. So this would be slow and this would be fast. Okay? How do I know that? Like if I look at the before picture, which is the top one, and then I look at the after picture, what do I notice about the wave in the after picture?
Not all of, I wrote the diagram wrong.
Okay,
It's thinner.
it's thinner,
I think so.
like this is thinner?
No, like the. Never mind, I must be super. Like this one.
Oh yeah, it's not as tall.
Yeah.
Yeah, yeah, exactly. This wave here, the one that's in the less dense medium, isn't as tall because it's longer. Yeah. If it's longer, then it has to be going faster. Okay, frequency can't change, so if the wavelength gets bigger, the speed has to have gotten bigger as well. Okay, that's how I can tell.
I just look at the before picture, I look at the after picture, and I can tell whether a wave sped up or slowed down based on how long it is and how tall it is. Okay? Now, if a lot of wave energy gets reflected, the height is going to be affected. Okay, because a lot of the energy is going to bounce back. Even if it slows down, it may not be taller because a lot of the energy is going to get reflected at the boundary. Okay, and that's what's going on here. Okay, if it goes from a fast medium to a slow medium, I get a much shorter wave, and the amplitude is reduced because most of the wave energy is here in the reflected pulse. Now, what do you notice about the reflected pulse when it went from slow to fast versus when it went from fast to slow? It's reversed. Okay? If you get reflection off of a boundary between or from a slow medium to a fast medium, the reflection will be upright. That is, it will look the same as the incoming and outgoing waves. If you're going from a slow medium to a from a fast medium to a slow medium, then the reflection will be inverted. Because it's harder for it to go into that, and so more of it gets reflected off the boundary.
Why? Because it still can't, like, so all of the wave energy can't go through from the slow to the fast.
Mhm.
It is the same the other way around. So why aren't both of them reversed then? Like both
I don't
of
think
the
I have an
reflected-
answer for why. To be perfectly honest, I don't think I have an answer for why. Just that they do. It's a good question. I'll look into that as to why. My guess would be that when it's going into something easier, less gets reflected. There's less difficulty, so our reflection comes back different. Okay? When we reflect off of a fixed end, it's always inverted because it's too dense and it just can't get in. Right? So, I'll have to look into that one. That's a good question. Okay? For now, just know that if it goes into a more dense medium, you'll get an inverted reflection. Okay? If it goes into a less dense medium, you'll get an upright reflection. Sometimes, some worksheets and some books, just so you're aware, will call the upright wave an erect wave. Okay, I don't know why. Upright and inverted seems to work just fine, but sometimes they'll use the word erect wave. I don't because people giggle. Okay, so just if it says upright or if it says erect, it means upright or the same. Okay, all right, everyone okay with that? I'm going to look into that one because that's a good question. All right, so I'm going to show you this. I'm going to put two of the Slinkies together, but they're going to be different. Okay? All right. Okay, so if wave energy reflects off, like we said, a more dense medium, okay, then it'll come back inverted, okay, like a water wave off of a cliff, okay, because rock would be infinitely dense compared to the water that the wave was traveling in. Reflection off a less dense medium results in an upright, okay, sound from water to air, okay, would be an example of that.